Today is the first day of Unit 10, which today's lesson is titled Exponential Functions, and today we're going to focus on graphing these. So far this year in Algebra 1, we have discussed two different types of parent functions. The first parent function we talked about was linear, and that made a line. Then we talked about quadratic functions, and remember quadratic functions are parabolas, which are in the shape of a U. Today we're dealing with exponential functions, and all exponential functions follow the shape of an exponential curve. So before we start graphing these, we're going to start by using our calculator to approximate the values of 1 through 4. So make sure you have your calculator with you. To do number 4, we're going to type in 4 to the 1.7 power. So in my calculator, I would go to my scratch pad and I would type 4. The caret button on the 2 to the left of 4 will raise your power to an exponent, and then we're going to type in 1.7. The calculator gives me 10.5561, and the instructions say to round to the nearest hundredth. So remember your places. You have your tenths place, hundredths place, and then thousandths place. We are rounding to the hundredths place, so the 6 bumps the 5 up to a 6. Our answer for number 1 is 10.56. Now look at number 2. If you look at number 2, the 2/3, this whole thing is considered our base, and then the negative 1.2 is considered our exponent. So in our calculator, we're going to put in parentheses 2/3, and then I'm going to hit the caret button and raise it to the negative 1.2 power. The calculator gives us this as our answer, which rounds to 1.63. The 6 bumps the 2 up to a 3. Now, number 3, we've talked about this quite a bit this year. Number 3, they have not put parentheses around the base of negative 3. So we're going to type it into our calculator just like it looks. We have negative 3 to the 1.6 power. Be careful, there is a difference between this and using parentheses to put negative 3 to the 1.6 power. This one, the question they gave us, did not have parentheses, so we're going to go with the negative answer. And then watch what happens whenever you round this. The 9 is going to bump this 9 to a 10, which is going to bump the 7 to an 8. So be really careful with your rounding. We're going to write this as negative 5.80. Moving on to the last one, we have 2 to the 2/3 power. You have to be really careful when you plug this in because 2/3, that whole thing is your exponent. So when you type this into your calculator, your base is 2, and then you're raising it to the 2/3 power. I would recommend putting it in parentheses to be sure that the whole thing of 2/3 gets included in the exponent. Our answer here, 1.5874. The 7 is going to bump the 8 to a 9. So we're going to put 1.59. The main thing you need to remember when you plug these into your calculator is what part is the base, or the bigger number, and what part is the exponent. Make sure you're plugging it all into the right place. All right, now we're going to start graphing these, and we're going to start with 4 to the x power. What I want to do first is talk about what that means if you were to graph this by hand. So first, we're going to make a table by hand, and we're going to start plugging in values ourselves. So we're going to start with 0 in the middle, and then we're going to move 2 to the left and to the right. So first, I'm going to plug in 0 for x, and look what happens when you plug in 0 for x. 4 to the 0 power, this is where your exponent rules come in back from Unit 6. Remember, anything to the 0 power is 1. So 4 to the 0 power becomes 1. Then I'm going to keep going. I'm going to plug in 1 for x. 4 to the first power is just 4. And 4 to the second power is 16. Now watch what happens when I go the other direction. If I plug in 4 to the negative 1 power, that's when your laws of exponents come in, again from Unit 6. Remember, anytime you have a negative exponent, to make it positive, you have to move it to the denominator. So 4 to the negative 1 becomes 1 over 4. Same thing with negative 2. 4 to the negative 2 power becomes 1 over 4 squared, which is the same thing as 1 over 16. So this is kind of why we're getting these numbers. So to plot this, first I'm going to plot 0, 1. Then I'm going to plot 1, 4. 2, 16 will be way off my graph. Negative 1, 1/4 is about right here. And negative 1, 1/16 is even closer to the x-axis. If you look at this, we can plug this into our calculator as well. I can go to the graph and I can type in 4 caret x. You can see that this curve gets closer and closer and closer and closer to the x-axis, but it never actually crosses the x-axis. You can check this by hitting Control T. If you look at this, as you go into the negative numbers, 1/4 is the same as 0.25. 1 over 16 is the same thing as 0.0625. If you look, it's getting closer and closer to 0, but it's never actually crossing 0. The reason for that is because you cannot have a base of 4 and get out 0. So the x-axis here is what we call an asymptote. An asymptote, it's listed right here on the right, is the line that it cannot cross. And we're going to talk about that more in a second. But what I want you to do is draw a dotted line over your x-axis because that's representing the asymptote. This is a horizontal asymptote. Our curve cannot cross the x-axis. So when you draw the curve, it's going to get closer and closer and closer to 0, but it should never actually cross 0. In fact, I'm going to draw mine a little bit better. So it never actually crosses. It almost levels off at the x-axis. So let's talk about the blanks to the right of this. Your y-intercept is like it's been all year. It's where it crosses the y-axis. So for this problem, our y-intercept is 0, 1. The asymptote is what we just talked about. It's the line that you cannot cross. So in this case, the line we cannot cross is our x-axis. We're going to write this as an equation of our line. Since this is a horizontal line, we know from back in the first semester that horizontal lines are written as y equals, and in this case, y equals 0. So I will never get out 0 for this graph. Now, talking about domain and range, we've done this before back in the first semester as well. Remember, domain is how you're moving from the left to the right. As I move to the left, it's going to keep going forever. And as I move to the right, even though it looks like it's just going to go straight up, it does get wider and wider to the right gradually. So my domain for this problem is all real numbers. Then for my range, I'm starting at 0 and going up forever, but I cannot equal 0. So the way we're going to write this, since the range is bottom to top, I'm going to write this as y is greater than 0. It cannot equal 0. It's everything above 0. Now, the last blank says, is this a growth problem or is this a decay problem? Since this is growing as we move to the right, this is considered a growth problem. And let's talk about the difference between the two real quick. A growth problem is going to look like this. The curve grows as it moves to the right. A decay problem is going to be the opposite, where it stops growing. Now, before we move on, I want to talk about transformations for a second, because the transformations for exponential graphs are very similar to the transformations on our quadratic functions. So let's play with our calculator for a second. Let's get rid of the table, hit Control T, and I want to compare a couple graphs to 4 to the x. So starting with, if you double click, I want to first type in 4 to the x plus 3. When you look at this, you can see that the plus 3 moved the graph up 3. This is similar to what we looked at with our parent function on quadratics. Plus 3 makes it move up 3, and if you change this to minus, it moves it down 3. So your asymptote can move based on the function that you have. So if it's outside of the exponent, it's going to move it up and down. But look what happens whenever I change, or I put plus 3 with the exponent. Now it's up here with the x. The plus 3, just like our quadratics, are very similar to our quadratics, moves it left 3. If I change this to minus 3, it's going to move it right 3. So just to kind of review some of our transformations, those are still happening here. Now, let's look at number 6. Number 6 has a different base. This time we have a base of 4. So if you were going to plug these in by hand, instead of using 4 as the base like we did on number 5, now my base is 2. Let's see what happens when we graph this in our calculator. So remember, doc B will clear your graph really quick. And let's type in 2 to the x power. Then you have to be really careful. The plus 4 is not included in the exponent here. The plus 4 is outside of the exponent. So you have to move the right arrow, bring your cursor down, and then put plus 4. You want it to look exactly like the question you're given. This plus 4 is not with the x in the exponent. It's outside of it. So based on what we just talked about, the plus 4 should move our graph up 4. And if you look at this, it definitely does. Plus 4 moves it up 4. Now the plus 4 is also important because it also tells you where your asymptote is going to be. My asymptote is no longer the x-axis. If you look, I'm leveling off here and now at positive 4. It might be easier for you to see what this means by looking at the table. So if you scroll up on your table, you can see as you move up that you're getting closer and closer to 4, but you're never actually crossing 4. So on your graph, you need to start by drawing in your asymptote at positive 4. I can never cross this line. Now I'm going to fill in the points from my graph. I'm going to scroll back down. Now, 2 to the 0 power would be 1, but remember we're adding 4 to everything, so that's why I have 0, 5. I'm going to plot that on my graph. Then I have 1, 6, and 2, 8. And I can even plot negative 1, 4.5 right in between 4 and 5. So again, I'm getting closer and closer and closer to 4, but I'm never actually crossing 4. Take a second, pause the video, and try to fill in the blanks to the right, and then check with me after. Okay, so your y-intercept on this graph is 0, 5. The asymptote that we just talked about, remember it's a horizontal line, so we write that as y equals 4. I can never cross 4. The domain goes left forever and right forever, so it's all real numbers. And then this time for the range, I'm starting at 4 and then I'm going up forever. I cannot equal 4, so y is greater than 4. This again is an example of a growth problem. Let's move on to number 7. Number 7, we now have a base of 3, but this one's a little bit different because it's being multiplied by 2. So when you plug this into your graph, Doc B again will clear it. We're going to type in 2 times 3 caret x. 2 times 3 to the x. Now, if you notice, but from before with quadratics, when we multiplied by a whole number, that made it have a vertical stretch. That's kind of happening here too, because 3 to the 0 power would give us 1. But when I multiply that by 2, it becomes 2. It's stretching it upwards. The asymptote here is still the x-axis. It has not moved up or down at all. So I cannot cross 0. You can double check this by hitting Control T. If you scroll up, you can see that I get closer and closer to 0, but I never actually cross 0. So to begin our graph, let's draw the asymptote, the dotted line, over the x-axis. This is just a reminder that you cannot cross the x-axis. The first point I'm going to plot is the 0, 2, and then I'm going to plot 1, 6. Let's see if we can fit anything else. 218 will not fit. -1 and then 0.66667. You can kind of estimate where that would be on your graph. It's a little over 1/2. But basically, this is again showing that I'm getting closer and closer and closer to 0, but I'm never actually crossing 0. Take a second, pause the video, and try to fill in the blanks to the right, and then check with me. All right, the y-intercept should be where it crosses the y-axis, so in this case, 0, 2. Your asymptote is your x-axis because we didn't move up or down at all, so the horizontal line for that would be y equals 0. I move left and right forever, so my domain is all real numbers. And since my asymptote is at 0, I'm starting at 0 and moving up forever. So my range is y is greater than 0. And again, this is a growth problem. It goes up as we move to the right. Now we're to our last problem, and we have a base of 3 for this problem. Let's plug this into our graph and see what it looks like. So hit Doc B, and then on the graph, we're going to type in 3 caret, and now here you have to be really careful because the 2x minus 1, this is all included in the exponent. This is different from what we did on number 6. On number 6, the plus 4 was outside of the exponent. But here, 2x minus 1, this is all included in the exponent. So I'm going to type in, if you want to put it in parentheses to be safe, 2x minus 1 all as my exponent. So the minus 1, that remember, since it's part of the exponent, moves it left and right. It doesn't necessarily move it up and down. So if you look here, it looks like our asymptote is still the x-axis. You can hit Control T and check your table to make sure. If you scroll up, again, you can see it's getting closer and closer to 0, but it never actually hits. So I'm going to first start by writing my dotted line over the x-axis because that's my asymptote. And then I'm going to start plotting my points. So the first point I'm going to plot is 1, 3. And then I have 227, which is going to be way off my graph. And 0.333, we can estimate where that would be, just about not quite at halfway through. And then I'm going to get closer and closer and closer to 0, but I'm never going to actually cross. All right, so again, pause the video, try to fill in the blanks to the right, and then we'll check it. The y-intercept that you should have gotten is 0. You can write it as 0.33 repeating, or you can write it as 0 1/3 from our table. The asymptote is the x-axis again, so that is the equation y equals 0. I'm going left and right forever, so my domain is again all real numbers. Since I start at 0 and go up forever, I can't equal 0, but y is greater than 0. And again, this is an example of a growth problem. Now that you've finished this video, pick up the homework and try the problems. They're almost identical to these, so use your calculator to graph them and then fill in the missing blanks.